Hello, today I'll be speaking about neural interventional GRU-ODEs. My name is Helen. I'm a PhD student at Carnegie Mellon University, and this was work done with Yuan Xue and Andrew Dai at Google. Our motivation comes from the fact that data is often generated as a sporadically accumulating byproduct of existing systems, with missing values across dimension and time. This data can be observational, interventional, or a mixture of the two. In hospitals, for example, diagnostic measurements may be taken as needed, and treatments may be administered and recorded over a finite period of time. This type of data is challenging to model, as established time series methodologies, such as recurrent neural networks, usually do not proactively consider the impact of interventions and often assume fixed time intervals. To model observational data alongside interventional data, we extend a recent line of work on neural ODEs, which reparameterize models with discrete dynamics into a continuous framework. Recurrent neural networks are an example of such a model with discrete dynamics, where the hidden state is updated discretely as it rolls out forward in time. In the limit, the dynamics of these models' hidden state, h of t, can be parameterized by a neural network, f theta. Given an initial state, numerical ODE solvers can then roll out the state to any time. Neural ODE models have since been developed for data sampled irregularly across time and dimension, as well as continuous flows with discrete jumps sparked by stochastic observation events. Leveraging these recent advances in continuous time modeling, we propose neural interventional GRU-ODEs, or NIGO, to flexibly model passive observations alongside active interventions, which happen sporadically. In this model, observations provide information about the underlying state of the system, for example, a patient's temperature, whereas interventions drive changes in the underlying state, for example, when a doctor administers vasopressors. Our model seeks to capture the influence of the interventions on the latent state while also learning the dynamics of the system. Here's an example diagram of a sporadic data generating process. So interventions A can affect all future hidden states H, observations X are emitted from the H's, and not all time points necessarily have actions or observations associated with them, and they don't have to be at regular time points either. So in our method, the dynamics of the latent state are summarized in this differential equation. Observations X of t are modeled as points along a continuous flow, whereas interventions A of t are modeled as jumps. And then mu, sigma, and w are modeled using neural networks. W of t is a Wiener process, n of t is a counting process, and A of t is an embedding of the intervention given by the data. Note that this formulation is similar to that of jump diffusion processes. This algorithm describes how NIGO works. Similar to prior GRU-ODE Bayes work, it alternates between a prediction phase and a filtering phase. The prediction phase uses jump GRU-ODE, which we display on the right, and the filtering phase uses GRU-Bayes, which is an analog of a Bayesian update. Interventions drive jumps in the dynamics given by the jump GRU-ODE, and the adjoint method for neural jump SDEs is used for learning. By proactively feeding in interventions as input instead of sampling them and then computing the likelihood, we are able to incorporate this as prior knowledge, and if the model is assumed correct, which is a big assumption, we could even interpret causal effects of this intervention. Finally, the loss is the weighted sum of the pre-Bayes loss and the post-Bayes loss. The pre-Bayes loss is a negative log likelihood of the data, and the post-Bayes loss is a KL divergence between the GRU-Bayes prediction and the posterior probability of the observations. Our experiments are conducted using OpenAI Gym's pendulum simulator. The data is uniformly at random masked, and the intervention is halving the simulator's gravity. This is also uniformly at random sampled for 1% of the time points. Across 3 trials, we note that NIGO achieves a mean squared error on average of 0.0022, and then GRU-ODE of a comparable network's architecture and size achieves an MSE of 0.0026. Qualitatively, NIGO yields smoother trajectories. In future work, however, we would like to explore how different hyperparameter configurations or learning methods can influence the dynamics being learned. We would like to explore further the trade-off between learning long-range dynamics versus immediate Bayesian updates, and also experiment on other settings with both observational and interventional data. And here's a summary of our work. Thank you for your time.